Hello and welcome back to Calculus 3, section 13.5, lines and planes in space, meaning lines and planes in R3. So your good old 2D space, R2, was all one plane, which was the XY plane, and in that one you had your two-dimensional lines, which were governed by y x plus b. So for R2, there's lag. I wrote R2. Now let's hope it works. So for R2 space, we had the entire space to actually be a plane, which was xy. And if a line in it, which was infinite line going two ways, you would label that one as y equal mx plus b. It will have a formula where b is the y-intercept. And the whole thing over here would be called the xy plane. So we do have 2D line and plane happening. Now, even though plane are these surfaces, we are going to define a plane exactly, right, using our Calc3. So now in R3 space, you are going to have, in a three-dimensional system like this, you are still going to have some kind of a line. And that line will have an equation. It's going to be infinite. So we will study that. The line is, again, something that has just length, so it's technically one-dimensional object, but because you can rotate that line in any way, the equation that describes this line will have to have x, y, and z, so it would be three-dimensional. So we say that this is a line in three-dimensional space, but you have to understand that point has no dimension to it. It's just a point in space, and point can live in any dimension. So you have a point in one-dimensional space, let's say 0, and that's a point on the one-dimensional line. But you also have a point at the origin of the two-dimensional space, and now that point is 0, 0. So the point shows the location, and it inherits the amount of dimensions that the space. So now line is a one-dimensional entity. It just has length. So if I take a cord, like this cord that powers my tablet, if I take this cord in this much is 2 feet in length, let's say. So 2 feet in length, and I can just think of it as a number line, and it's just 0 to 2. But the trick is that since I am in a three-dimensional space over here, I can orient that line in any way I want, and it's still 2 feet long, right? But the trick is that I cannot describe that line as 0 to 2 anymore, because now it is taking a slanted direction in terms of the origin of where it was before. So there is the line that goes from 0 to 2 on x-axis, and line that goes from 0 to 2 on y-axis are not the same line segment, because yes, they do have the same length, but they don't have the same orientation. So they will have a different equation in 3D space. So that y equal mx plus b, which is the three-dimensional equivalent to that, would be different for the line segments of the same length if they are oriented differently. And the second concept we are covering now is the concept of a plane. So I can have a plane that sits, let's say, plane that sits at an angle, right, in x, y, z plane, and it's we need also to figure out an equation for a plane. So the plane, let's say, lowercase p. So let's start talking about these two concepts. The first one is line R R3. You already know R2 line y equal mx plus b. Now let's talk about line in R3. So the way we're going to describe the line in R3 is to pin 2 points. So this is something that cannot change regardless of dimensions you're in. Every line can be perfectly described by only 2 points. If you need to stretch a string between 2 points, right? If you need to stretch a string, all you need is the 2 points. So one for one end, one for the other end, and then the line will shoot through those. So if I have my throw-dimensional coordinate system over here, x, y, z, and I pick 2 points in space, call the first point over here on the left P0, which has x0, y0, z0 coordinates, and call the other point P, just x, y, z. That's the one that you are allowing to move. As soon as you, so this is called a fixed point, and this is the variable point because it can go along. So now you can strike the line through these 2 points, and we'll call this the line L. So all you need in space are 2 points, and you're done. Now we know that any point you draw on the system is going to have a vector stretching from the origin that would show location of that point. So what I can do is I can draw a vector connecting into P, and we'll label that vector R for now, and that vector will clearly have x, y, z coordinates in 3D because you are subtracting 0, 0. Remember, it's a terminal point minus initial point. Initial point is 0, 0, 0. So whatever the coordinates of the terminal point are, those would be your coordinates for the vector, right? So x, y, z, and then another vector stretching from origin to P0. We'll call that vector R0, and clearly that one is x0, y0, z0 coordinates for this vector. So let me just, so that's our R0 vector. Now, if you take a look at these 2 vectors, I'm also going to create another vector along the line over here, as green vector with the arrow, and I'm going to label that vector as TV. So it doesn't make sense right now, but eventually it will. So if you carefully look at the diagram and you consider a vector addition, you will see that R0 vector plus TV vector will create vector R. So by looking at this here, you can write the equation R0 vector plus TV vector. T is not a vector, T is just, well, we'll see what the T is. Just put the arrow above V, and then equals to vector R. Now, if I rearrange this equation and write it as R equals TV plus R0, sorry, no, not VT. VT. I'm going to swap this. I'm going to put the vector first and then the T later. If I just rewrite it, so it's the same equation, I just rearranged the terms. Doesn't this remind you of y equal mx plus b? And this T serves as an input. You can think of it as time. At 1 second, you are maybe here. 1 second later, you are maybe there. Another second later, you are maybe at the point P. So the t would allow you to travel in time along this line. So as you can see, the comparison between these two equations. Guys, this is equation of the line in any dimensional space. This is equation for the 2 dimensions because it would reduce to this. It is equation for the 3-dimensional space, which we are studying right now, but this equation also works for 4D and 70D and 100D space. So this is the nth dimensional equation for the line. That's the big boss, right? And as you can see, it was very easy to get that equation. The only clever trick that we had to do was to call this TV. So now, what is happening here? Well, each one of these vectors has 3 elements in them. And something you learn in linear algebra is that you can write your vectors as a row vectors, or, which is what we always do in Calculus 3, and we will always write them as row vectors, but you can also write vectors as a column vectors. So you can write your vectors as a stack, x, y, z, rather than writing them as like this, x, y, z, right? So this one over here is called a row, right? That's a row vector on the bottom, and this one over here is called a column vector because they are arranged in a column. It's the same thing, it's just the way we write them. Now, if you go to the next one, we'll call A, B, C components of this mysterious vector V times T plus, and R0 is X0, Y0, Z0 as a column vector. What you are getting here are 3 separate equations, which are, as you are all expecting, 3 parametric equations in terms of t that describe the line. You have equation for x coordinate, which is at plus x0. You have an equation for y coordinate, which is bt plus y0. An equation for z coordinate, which is ct plus z0. And because r was equal to that, and you know that each one of these is a separate vector, you can write this. Well, no, we'll deal with that later. Next chapter. Don't worry about it. We are done. This is your equation of the line. The thing that I am skipping now is to write this in a vector r, but that's the next chapter. So we'll deal with that on Monday. So what you have in this box is equations, plural, equations of a line in 3D. Clearly, if you have a 4D, there will be another row. For 17D, you will have 17 equations. All of these equations are coupled because they all depend on the same parameter t. Yes, each dimension is for itself, but they are all connected through t. There is another way to describe the system. So this is, I'm just going to say, line in R3, right? So that's the line in R3. Come on, update. Never, I just wrote line in R3. So that's the line in R3. And there is another way to write this, which pretty much no one uses, but I saw some problems that are went offline. Yeah, it looks like the bandwidth today is going to be a challenge. So if the video for this lecture gets messed up, you have my older streams. They're going to have different examples, but yeah, it's going to go in and out, in and out. I really don't know what. I never watched any of these. There's 1,200 of these lectures on my channel. I haven't seen a single one of them. And I keep telling myself that I want to go and watch, was it Tuesday's Calc2, just for the first 10 seconds to see if the stream is not starting with a sneeze. Because as soon as I started a sneeze and I was about to say, hello, right? As soon as I was like going like this, the student over there goes, yeah, right? And I was like, wow, nice. So let's see if the stream actually starts with a sneeze, and for them to someone pose a problem for you. You solve each one of these for t, and then you equal these into a three-sided equality, three-sided equality. So the t from the first equation is obviously x minus x0 over a. T from the second equation is y minus y0 over b. And t from the third equation is z minus z0 over c. So that's what we have when you solve for t in each one of these. And because it's t equals, and t equals, just equal them all together to get x minus x0 over a is equal to y minus y0 over b is equal to z minus z0 over c. And that's also a way to show it's a three-sided equality. And again, you have to have all three pieces. You can't just have two of them or one of them. You have to have all three to describe a line. So this is just another form. And as I said, it's going to be very rare for you to run into this. But then some homework problems and probably my MATLAB problems are going to be posed this way. Now, I will not be bothering you with this form on the exam. But again, you might run into this in your coursework later in engineering and so on. So this is the derivation for the line. And now we can just do a whole bunch of problems figuring out the equation of the line if you are given the points and good stuff. Now, first of all, I want to go back and talk a little bit about this TV term that we just out of nowhere placed there, and what is the significance of that. Well, first of all, you didn't have to put a TV there. You could have just put whatever you wanted. You could have just put vector m and whatever. See, this vector v is multiplied by a scalar quantity t. So we don't have to worry about t. We saw that t worked out to be our parameter for parametric equations that we got. But we don't have to worry about t in the explanation because it's a scalar quantity that multiplies vector v. What is vector v? That's the question. And the green vector v that stretches from p0 to p is a three-dimensional slope. That vector carries the directional slope of the line in the 3D because that green vector goes along the black line, which is your line L. So in some sense, the way that m was the slope for your line in algebra, now this vector v is a three-dimensional version of that slope, but it's actually a vector. And it gives the direction, and we see that we can always find that vector v, well, as we can't see, that vector v you can always get by subtracting the 2 points p0 and p to come up with the right location. So the most fundamental problem over here would be to find the equation of the line going through 2 points that are given in space. So find equation of the line. And when I say equation, I mean all three. Find the parametric set of equations is just lazy to write all of that stuff. So find the equation of the line, find all three parametric equations of the line going through, and then you just come up with whatever points you want, 2, negative 3, 4, and negative 1, 6, 2, whatever, doesn't matter. Okay? So guys, if you spend 6 minutes studying the diagram, and you would immediately see that the 2 points that you have, right, one of these, it doesn't matter which one you pick to be whatever. So one of these points, let's say this one is -1, 6, 2, and the other point would be 2, -3, 4. Now, can you draw this exactly through the? Sure, but no one cares. The most important part here is to pick, and that depends on you. Pick which of the 2 points you want to be the fixed point. That's extremely important because that's your P0 and that's going to be your X0, Y0, Z0. It's important because there is a calculation that will depend on your choice. You are allowed to choose any of the 2 points, but you have to stick with it through the end of calculations. So if I pick this to be my P0, which is the fixed point, then that means that my X0 is -1, Y0 is 6, and Z0 is 2. So this is something that it's important. Now, reason why you have to pick that is because your green vector TV, right, is going to emerge from P0. Therefore, the vector V, which you need, right, you will multiply it by T later. Vector V you need is going to be the point, it's going to be vector P0P, which means that you will be subtracting P minus P0, right, to get your vector V. That is the reason why you must specify which one is your P0, because it's always going to be P minus P0, and P0 gives you X0, Y0, Z0 to plug in your equations. So this vector is 2 minus -1 is 3, -3 minus 6 is -9, 4 minus 2 is 2. That was our first lesson of vectors. When you have 2 points, to stretch a vector between 2 points is terminal minus initial. Now I have my vector V, which means that I have a TV because each one of these times T. So TV is going to be 3T, -9T, and 2T. So I have my X0, Y0, Z0, I have my TVs. Guys, if you look at your equation, you can just write it out. And I'm just locked over here. I'm just going to write this on the board because I think my tablet froze because of the internet trying to connect and disconnect and connect and disconnect. So I think it won't write on the screen. So to finish off this problem, you have to write x equals, your x0 is -1, so -1 plus 3t. Your y is y0, which is 6 minus 9t. And z is 2 plus 2t. All three together as a set. Remember, it's a parametric set of 3 equations for 3 dimensions. And this would be your problem solved. That's the way you do the problem when you have 2 points to find the equation of the line. It's interesting. Some features are working, but scrolling and writing doesn't work, but I can pick different colors. I have notification that the stream is down. All right. Well, the writing is back, so I can actually write the answer. Well, that worked too. Okay, but there is lag. Network is acting up. So -1 plus 3t, y equals 6 minus 9t, and z equals 2 plus 2t, and that would be the answer. So all three equations coupled together to create one line in space, in 3D space. So I would encourage you to try and give yourself two-dimensional points. Give yourself two-dimensional points in space, not in space, in plane, and use the same Calc3 method to come up with a parametric set for lines. Then set the t's equal to each other and come up with y equal mx plus b from there, and then do the algebra way, y equal mx plus b with 2 points, and you do the slope y2 minus y1 and all that stuff. You have to get the same line. As I said, this method that we learned, this is for n-dimensional space, and 2D is assumed in it. So this method works for 2D and 3D and 4D. We are only using it for 3D, but it should work for all dimensions equally. So that's the way to figure out the line. And now the next part of figuring out these lines is the line segment. Line segment. So this line that you see over here is infinite. You get to pick any t you want, positive, negative value, and it will go and go and go and go forever. Now for the line segment, which is finite line, right? Line of the finite length. You guys get to so line segment, finite line. You guys get to limit the line by simply limiting t. If you limit your t from, let's say, 0 to 2, then your line will have endpoints, and this is the part that you need to know and need to have in order for you guys to be able to do your chapter 17, line integrals. Line integrals are on a line segment, right? Finite length. That's why it's line segment. So the line segment is going to have the same equations: x0 plus at, y is y0 plus bt, and z is z0 plus ct, added that t is going to be between values, let's call them t1 and t2. So all together like this, and this over here is the part, so part which limits the line. So now, say you have x equals 3 plus 2t, y equals -2 plus t, and z equals 6 minus 3t. And you are on 0, less than t, less than 2. You can calculate endpoints for this line by simply plugging in zeros everywhere and 2's everywhere. So endpoints will be calculated by plug in t equals 0. So that point would be when t is equal to 0, it kills all t's, so it's just 3 negative 6. And then plug in t equals to 2, that's 7, 0, 0. And you can quickly graph these 2 points in space and then just connect those 2 points with a straight line, and you guys will have the line segment. Line segments, as I mentioned already, are finite. They go from one endpoint to another endpoint, and they have the same equation as lines, but they have the extra piece, which is the piece which limits them. So that will be the line segment piece. And they do have this equation, which I'm not going to bother you with, equation with the distance between two points. You can just use the distance formula. Well, hopefully it reconnects. You can just use the distance formula for distance between any 2 points on the line. And then there is the formula that they give in a book to calculate the distance between a line and a point. When you are calculating distance, it is assumed that you are talking about perpendicular, orthogonal distance. If you have a line in space, and you have a point somewhere in space, so if you have a point somewhere in space, clearly all of these are distances between line and a point, and clearly there is infinitely many of them, right? So there is only one special distance, and that one special distance is the perpendicular line that will stretch. So this one that has 90 degrees. So that's the distance d that they want to calculate. So anytime when you hear what is the distance of a line to the point to the line, they are thinking of the closest. Now, the straight line is the shortest distance. Today, we are going to see later on when we talk about surfaces that on a curved surface, straight lines are not the shortest distance. They're longer, which is why planes do not fly in a straight line. But we'll deal with that later. So they give you the formula for this. I would encourage you to actually figure out the method of calculating this rather than memorizing the formula, because formula takes the soul out of the whole procedure. So the distance d, the formula that they give you, I actually don't know this formula because I don't care about it. When I need to compute this, well, I don't need to compute this ever, but when I need to compute this to show someone that it can be done without, I just use the notions of perpendicular product. You have the dot product, you have the cross product, and all that good stuff. So V cross PQ divided by V. Hopefully that thing reconnects. So you have your distance, and then you have your you know that your vector v is the green vector that goes and runs along the line over here, and the unknown point is the point Q. There's a point P. Oh. Just reading the diagram, it's a formula, but as I said, it's much nicer if you actually break your head a little bit to establish the way to calculate this using the cross products and things rather than memorizing the formula, which takes out any thinking out of the equation. The second part of this lecture is about planes, which are the two-dimensional flat surfaces, like the surface of the board, surface of the tablet, surface of your desk, or the floor, or the wall in our classroom. So, planes in R3. So I already told you that the two-dimensional space R2 that you have been dealing so far in mathematics contains XY place and XY plane, and that one is what you studied so far. But now in R3, you can orient the plane any way you want. We already agreed that we will be walking on XY plane because we put the x-axis and y-axis along the walls, which creates our floor to be XY plane. But then we also have XZ plane, which is that wall, and YZ plane, which is this wall. Now, the ceiling over there is also a form of XY plane, but it's elevated, and we need a way to measure that. So when we talk about planes and set some things up, we will actually describe this classroom entirely using mathematical equations. All right, so where do we... And obviously that is very important because you want to model things on the computer, you want to use AutoCAD, you want to use all other software that does drafting and then eventually simulation as well. And also you want to create video games, you want to create environments, you need to make the engine in which artists are going to create video games that you guys play. So there's a lot of very important applications to this, for which P0 P vector